next installment of our Power Session webinar. Today we'll be looking at the state and outlook for nuclear generation. But before we do, we have a few housekeeping matters. So I'll be taking you through this presentation. It's going to be recorded and distributed to all attendees at the end of the presentation, most likely tomorrow morning though. Please feel free to forward it on to anyone you think might be interested. You are welcome to add your questions to the chat as we go. My colleague Sarah Gonzalez is monitoring the chat for the Q&A session and will help me steward the questions at the end of it. Now, please don't forget to vote for your next favorite topic for the next webinar for us to cover. We really do listen to people's views as to what would be of most interest. And so please make your voices heard. Now, without further ado, we'll get on to the topics of nuclear policy, the key technologies and performance indicators, its relative competitiveness, and then we will talk about key takeaways and recommendations before Q&A. So I'm Ezra Beeman. I'm Managing Director of Energea. We've got offices in Sydney, Australia, and in Davis, California. So first of all, I'd like to acknowledge that these graphics are not necessarily state of the art, but it's very difficult to find any on small modular reactors because they really haven't been built yet. There's two that have been built, and that's not exactly like those are easily accessible in stock footage. So that's why we are showing these. All right, let's start with Australia's policy. As everybody on the call, I'm sure knows, Australia has its net zero targets. Now I have to apologize here as well. I know they were just republished, and we haven't had time to update them. That being said, these reflect the Kyoto and Paris Agreement targets, as well as those set by the Climate Change Authority back in 2000. The Climate Targets Panel back in 2021. So as of now, it is prohibited in Australia to be building a nuclear installation outside of the one that our Panza runs, which I understand keeps the door open for the technology for Australia. I actually, incidentally, knew the project manager still know him for that project. Despite not having any nuclear capacity as such in Australia, given the transition to zero carbon and that nuclear technology is classified as a non-emitting technology, there has been a discussion in Australia, usually every election cycle, around what the potential role of nuclear technology might be in achieving those goals. And so that's one of the reasons why we decided to take on this topic. There's a lot of information out there. My own view is that it often comes with a lot of political viewpoints. And so we really just wanted to play it with a straight bat as much as we could and have a look and see what we found. So when we look around the world and we explore what the rest of the nuclear club is doing with respect to its nuclear fleet and its nuclear technology, you can see there's a wide range of positions being taken in terms of new capacity. And one of the most interesting things from my perspective is that neither Japan nor Canada actually have set any new nuclear targets, while others, including China and others, but mostly China, is looking for a sort of a really massive build out there. I mean, the U.S. has got another target of 300 gigawatts by 2050, which would triple our current capacity in the United States. Most of the other targets are a little bit more modest. India is the next largest after that, which is about 90 to 95 gigawatts by 2047. Some of them are targeting export markets like China and South Korea, but most of it's domestically focused. Now, in order to achieve those sorts of numbers, clearly there's going to be have to be some incentives, and they vary. I mean, some countries like France are pretty much underwriting it all by the government, and then are going to add a levy onto bills. Other jurisdictions are looking to offer different budgets within government organizations. The one I found most interesting was up to a $7.5 million loan in South Korea, and I'm not exactly sure how much of a nuclear project that's going to buy, but there you go. All right. So one thing to become knowledgeable around nuclear technology are the different types of reactors, and so I wanted to start with a series of definitions because you will be using these terms further on in the presentation. You've got the most common reactors are the pressurized water reactor and the boiling water reactor, and I won't go into the details here of the definitions, mostly because you can read it at your own pace, but only to call out that these first two represent, and I'll show you the actual market share in a second, the lion's share of nuclear deployments to date. Now, an increasingly popular concept out there in the media, at least, is the small modular reactor. One thing I learned in preparing for this webinar is that it is not a particular type of reactor. Rather, it is an approach or a design philosophy to deliver standardized, lower footprint, lower price tag, and quicker uh, construction times compared to conventional approaches. Now, the other thing to call to your attention are the so-called Generation 4 reactors, and they each are taking different approaches to deal with some of the what are seen as drawbacks of the technology, including water consumption, waste, and other key attributes. It's very difficult, by the way, to get particular information about each of these, but we've done our best later on in the webinar. Now, a classic sort of design for a nuclear power station is shown in the top left for the pressurized water reactor. It's a two cycle um, generation technology. You've got the primary cycle there, which is heating up water. It goes into a steam generator, into a turbine, and out to a generator. Um, and that's the most common configuration. In terms of the actual capacity that has been deployed, you can see in the bottom left, mostly pressurized water reactor in red, and then boiling water reactor in orange, with a decent showing of the pressurized heavy water reactor there as well. Now, in terms of the timing of the deployment of this technology, I mean, these stations run for a long time. You can see there was a peak in building in the mid 80s, and that we're seeing, a rise since about 2010 of building uh, pretty much rising every year except for 2025, which isn't done yet. So there's definitely a revival that we're seeing in the actual capacity, um, and so I think it's premature to count this technology out by any means. Now, if we were to just compare the conventional approach to the small modular reactor, and in Australia, we have used the CSIRO numbers here, which range in their levelized costs from 140 to $233 per megawatt hour, and then we've compared that to a small modular reactor, also in Australian dollars, and we've taken this from the new scale SMR design, which is the only approved design in North America. Now, there are other designs, and I think you'll see later on that the cost of small modular reactors can be considerably lower, but it would be maybe in a jurisdiction that didn't have the same safety requirements and conditions on it that you would see in North America. So we decided to use the North American price tag here. We've shown build costs, which are different, but it's for a different kind of. These are dollars per megawatt. Um, but I guess I would say that you don't see a huge amount of penalty for a much smaller unit. I mean, the original conventional reactors were upwards of 1 gigawatt, whereas we're seeing a lot of the small modular reactors at the 30 megawatt sort of sizing, which is a very different proposition. in terms of risk and the whole and land use and water use, etc. In terms of the ramp rates, they are not much different, and that's one of the biggest challenges I think that we've seen for this technology. It really is a classic baseload technology that was designed to be operated pretty much all the time with a mid-merit and a peaking technology to load follow. Um, Large or high penetrations of renewable energy and its intermittency really is quite in contrast to the old system. In terms of minimum run, that's important because if you are being backed down just because there's low demand or low net demand, how much lower could you go before you actually have to have an outage or some kind of a restart, and what are the costs involved? In terms of the planned outages, these are for maintenance, about the same between the two technologies. Waste management's still an issue. Um, and in terms of the water requirements, liters per megawatt hour, the small modular reactors, at least this particular design, is looking to significantly reduce the requirements, but they're still not immaterial. Now, in terms of what's actually being proposed or built out there, we found two reactors that have been classified as small reactors operating. One is 70 megawatts in Russia, and then the other one is 210 megawatts in China. Now, in contrast to those two, we also identified a number of planned small modular reactors ranging from 32 megawatts in Argentina all the way up to 300 megawatts in Russia and Canada. And they're using a range of reactor technologies you can see there, mostly pressurized water reactor, but also sodium fast reactor and molten salt. um, Now, the build years there are, in my view, pretty aggressive, and we've shown you the completion years. So I don't think the world will have to wait too long to see whether or not these pilot projects are built in the time frames that they are showing here, and also for the budgets they are showing here. But if they are, that would represent a significant change in nuclear technology form factor and risk profile. All right. So when we line up all of the different reactor types, or a subset of them anyway, and we look at some of the key drivers of their competitiveness, including cost per megawatt, lead time, sizing in terms of minimum megawatts, the ramp rates, the maintenance time per year, the minimum load, water where we have it. We don't have anything for restart costs. And then the maturity, how many megawatts of this particular technology has been deployed and its lifetime. This is basically what we're seeing here. So the small modular reactors are promising to come on stream in a much shorter time period, which might just reflect the smaller form factor and capacity. But even so, that's a much faster response time to the 7.5 years shown above, which can actually take a fair bit longer in practice. Um, you can see here a range of sizings, um, and even a range in ramp rates, anywhere from 5% of megawatts per minute all the way up to 20%. And that would provide a much more, I guess, flexible resource than something that's only at 5% megawatts per minute. All right, now let's turn to the question of cost competitiveness. And we wanted to look at this a couple of ways, because you can't just look at levelized cost of energy anymore, which is, if you divide the total cost by the total output, because the actual shape of that output matters, and the impact of the resource on the wider system also matters. If the resource is inflexible, then other things need to be more flexible, because load is not constant, except in the case of data centers. We'll get to that. Likewise, if something is intermittent, then it needs to have something that firms it up, right? So none of these technology, I think, is a silver bullet, Open cycle gas turbines are great for load following. They're a little bit more expensive, and they also emit CO2. So nobody's perfect. So we first look at, and we're just using Queensland as an example. What is the actual load shape in Queensland? And this is using FY25 data from AMO. And so we just looked at, on average, what is the load shape in Queensland before any sort of generation, intermittent, et cetera. And then, how does it look in summer and how does it look in winter in this one particular year? Um, there's actually not a huge amount of difference there, which was a little bit surprising to me. The other thing we wanted to look at was the Queensland price duration curve. So, price duration curve takes the regional reference price for every hour or half hour and orders it from highest to lowest. And the reason why people do this is to try and understand um, at how often a plant could be dispatched depending on its bid prices. And it also helps see, the percentage of time that prices are at a certain level. So in this case, if we have a unit that really wants to be baseload on all the time, it's getting a lot of prices above zero, but there's also a fair amount of prices that are below zero. And in order to stay on, an inflexible unit will actually have to bid negative. And we see here that the bids range from just under negative 50 to around negative 50 for about 20% of the time. So that's one of the things to consider in with a relatively inflexible load, that it would be bidding a negative to stay online, and that's exactly what's happening here with the other thermal plants, because there is a cost to restart these. If you were to shut them off and then start them up in the morning, there's a cost associated with that. The one thing we'd say here is if a unit was operating today and was dispatched 100% of the time, and yes, it has to be taken out sometime for maintenance, but you will not always do that. When it's negative prices, you usually have to book out a couple of weeks. That at the moment in Queensland, you'd be earning about $109 per megawatt hour on average, which is slightly lower than the CSIRO pricing of 141 per megawatt hour um, for nuclear technology if it could be built. So then what we did, so this is just the current sort of situation, and um, it doesn't seem like in the current situation that the technology would be able to operate at least as a baseload unit. And we didn't. I mean, we this is a webinar, so we didn't have the scope or the budget to really dive into the detail of, well, what if they start ramping and what is the actual, what does that look like? But that would be something else to have a closer look at. Now we then turn to Queensland's bulk system in FY25, again, thanks to AMO's ISP from 2024. And you can see here's a little bit more of a duck curve, but the low is not as low as maybe some might believe, probably because batteries are. Actually, this is before we add in any batteries, so it must be behind the meter batteries that are operating here. And again, there's not a huge amount of difference between winter and summer, but that's the climate of Queensland. And then what we did is we took a linear solver with all of the gen cost prices and load shapes in Queensland, and we just did a simple sort of solution that identified, what would be the average dollar per megawatt hour for the load in FY45 using just solar storage and batteries. And then we added in a 30 megawatt SMR to see if it were able to lower the price or if it raised the price. And you can see here that it raised the price just a little bit. So don't take this as final. This is a relatively simple, but this is a technique we do use on simple cases, usually around resource optimization, where you look at the optimal portfolio of a resource for meeting all demand with constraints like no emissions. So the other thing I guess you could look at this is if nuclear could get its prices down by FY45 lower than what CSIRO is for, not CSIRO. Well, CSIRO may have done it, but the Gen Cost model, I don't think they did this year. Then it could be within striking distance, I suppose. Now, the other key potential application, and certainly one that's being looked at in the U.S., is using small modular reactors to meet data center load. And the reason why that could make a lot more sense is shown here in the top left. Now, this is from the UK Power Network's data center demand profile. And my initial question is, why is utilization like 25%? And it's because it's just been connected. And this is one of the things about data centers that I don't think people realize. It's like a major industrial park, right? Where there's the initial build out, but the whole thing gets built out over maybe 20 years. So if you connect, you know, 100 megawatts of of the load, you may not see 100 megawatts until like year 10 or even beyond. Anyway, that aside, you can see here that it's pretty much flat all the time, which is the standard data center load for reasons you can learn more about in our data center webinar. So what we first did is we say, okay, well, for that load, how much would it cost to serve it in NEM states in FY25? And we saw there was a range of prices here, and they're all sort of in between around 90 to 130 or 87 to 120, with most of them in the sort of 100 to 110 level. And again, that is a bit higher than the pricing that we saw for the CSIRO quoted numbers. Now, the other thing we looked at is with today's prices, how much would it cost to serve that load using nuclear only, a CCGT only, OCGT plus PV, and then a range of or two um, uh, PV wind combinations and battery systems. And what we found, now keep in mind that this is a 50 megawatt nameplate plant, but its peak demand at this stage is only 17 megawatts, which is why 17 is the number you see for the thermal firm sort of dispatching technologies. Now, in practice, nuclear is going to have to take an outage, and you're going to have to figure out how you're going to back that up. So it's not quite this simple. um, and the same with the CCGT. Now, we thought it was fair to just use those baseload units because they will be operating pretty much flat all year to match the load. And then we compared it to an open cycle in PV because there would be some ramping there when the PV is not available, et cetera. And those prices, are not too far off of each other, but they do, depend on certain prices for gas, which into the future as the country goes to zero carbon, are going to have to be replaced with things like either um, green hydrogen or biofuels, and it starts to get a lot more expensive. But again, the limitations on this particular webinar were such that we didn't explore all of that. Certainly something to look into if this is something that you really want to explore. All right. So the key takeaways, and just mindful of time to can have a couple of questions. So first of all, Australian law prohibits nuclear installations at the moment. Nevertheless, there's a great deal of capacity around the world that is going to be replaced at some point, as in the process of being replaced. Most countries are aiming to invest in next generation technology, or at least keep their options open. The small modular reactors do promise smaller form factors, faster construction times, and without too much of a cost penalty. So that could make them more attractive for today and tomorrow. Um, there are very few of these designs that have been certified to date, and that key limitations with the technology include, obviously waste management, water consumption, ramping rates, and restart costs. So surprising to me anyway. Number of pilots are currently underway, with significant results expected in the next 3 years or so. The high utilization baseload nature of the technology may find it hard to integrate into high renewable systems. But data centers with their flat loads could be a key future customer, especially where there are connection limitations. But access to water will be key. And finally, our analysis shows that the flat load profile makes it a modular reactor with competitive with solar plus wind plus battery, economically speaking, anyway. So, in terms of recommendations, it's pretty lightweight, given you can't actually build this in Australia. But we would recommend monitoring the outcomes of these reactor pilots to see how well they actually deliver on their promises. Because if they do, I do think you could see nuclear capacity at least maintain its current market shares, if not grow in some of the markets. For data centers and other major industrial loads, it's important to consider the value of flexibility to maximize the grid connection capacity and minimize standalone costs. I mean, I think one of the challenges and one of the openings for nuclear technology is where the grid cannot handle any more data centers, and yet the data center wants to be built. In which case, you'll need a standalone system, and nuclear might be very competitive in that scenario. Um, However, it'll be important to monitor the cost of alternative technologies, especially long duration storage. All right. Well, thank you very much. Hopefully, you got something out of that. I look forward to seeing, hearing your questions, and hopefully seeing you at our next webinar. Okay, we've got a double barrel question here. First is flexibility of nuclear reactors. In relation to xenon poisoning, so that's not something I am familiar with and have not actually heard of the xenon poisoning as an issue with flexibility. I am more familiar with the issue of ramping nuclear stations in France, for example, where they tend to get hotspots, and that tends to reduce their reliability. The compatibility to work in a mix of intermittent renewables. Well, this is the thing. Um, Intermittent when sun is shining and wind is blowing, the marginal cost is zero. But you're better off curtailing both of those rather than having a thermal unit like nuclear go offline because there are restart costs involved, and that's why those units will be negative. You'll curtail off solar and storage, sorry, solar and wind, or you can increase your battery charging. I mean, I think it is possible, and we're working with baseload units now. It leads to things like negative pricing. Do you expect that the pilots will hit their targets, or will we see the types of overruns that we have seen in conventional reactors? Well, that to me is the billion-dollar question. I mean, the other thing to bear in mind, and in fairness to people running pilots, even if they are nuclear power stations, is that pilots are, first of a kind, and almost always have challenges, whether they're technical or commercial, etc. So I would say if they do nail their target timelines and budgets, then I would be amazed, just because it is, immature technology at this stage. Haha. How long realistically to get approvals, design, construct, and supply an SMR in Australia if the law were amended? Look, that's a great question. The whole nuclear consulting industry is not what it was, just because the call for the technology is not what it once was. Um, I would have to look to the examples from the pilots, none of which are in the U.S., to be able to answer that question. But a really good question to know, because I expect it would not be a short process. Whoops, sorry, I finished that. The question was basically, um, what are the costs with reduce shutting down these plants on a seasonal basis? I mean, they shut down for maintenance anyway. Um, the cost for shutting it down overnight, or on a couple of months, I think is pretty much comparable. I mean, again, I don't have firsthand knowledge of nuclear stations, but I do have experience working with more conventional power plants, and um, as long as you keep them oiled and generally perform maintenance while they're shut down, I don't think it would be much more to shut them down for all summer, for example, when there's too much solar. Um, Thereby reducing some costs. But I mean, you're going to have fixed operating. You're just basically saving on variable operating costs and fuel, which is not a very large portion of a nuclear power station. Hey, so using nuclear to back data centers is intuitively sound, but having to back the nuclear for normal downtime for maintenance would increase costs significantly. I mean, I glossed over it, but this is the challenge. It's also a challenge for the grid, though. I mean, if we have a 100 megawatt data center and it goes down, like that's just a massive loss of load. I mean, that's on the other side of, well, how do you actually have to have a battery that can quickly come online to keep the system in balance. So yeah, how do you manage that? Is it a really really cheap biofuel burning open cycle or even reciprocating engine that's going to cover it while it's down? I mean, you don't want to have a battery. You're only using a small fraction of the time. I think a lot of it depends on if you're isolated or interconnected. Because if you're interconnected, you can trade, but then it has other issues. So yeah, I mean, I think it's something that's going to have to be worked through whoever does it. Just noting it's a minute past, so thank you everyone who's able to attend. I'll stick around for a couple more minutes and answer questions. But again, thank you, and please join us next time. And please forward this to anyone you think might gain some value from it. Back to the questions. Do you think that data centers will be able to shape their load to intermittent loads, and if so, by how much? Okay, so in our data center webinar, we alluded to the potential for more load shaping, and since that webinar, we also have read work by Google and others that are looking to shape more of their data center load to better align to renewable energy, so that they can be consuming renewable energy and not non-renewable energy. Um, as we said in the webinar, though, a lot depends on how much synchronous data processing has to happen. I mean, when you push a button, like you expect that transaction to go through, et cetera, Internet of Things, gaming, et cetera, like that has to happen when in real time. But there is a lot of the load that is batched and could be done at other times. So our own view is that there could be a lot more flexibility in demand in data centers in the future. But at the present time, only really the tier one players are even looking into it. Oh, sorry, did I just? I may have dismissed the question without answering it. Uh, Someone asked, if the plant shut down during periods when prices were negative or on average, wouldn't that create a savings? Yes, it would. So you can either pay the amount that you avoid at negative prices. Uh, Sorry, you can either shut down and avoid those prices or pay them. So as long as you bid whatever the cost of shutting down is, it's always going to come out the right way, right? Either you can stay online and pay less, or it's going to be more expensive than it costs you to shut down. So that's um, that's really the bid pattern that we would expect to see. Do you think that baseload generating technologies are no longer needed? That really depends on how much they cost. If they were really, really super cheap, it'd be like a wind resource, which even if you're not using it, you're putting it into the battery and using it later. So I think, I mean, when it's base load and it costs a lot to stop it and start it, then you're gonna have to be a little bit careful. But um, it's a complex analysis to understand how the system fits together. And when we do it, we're using a nonlinear solver, and that's a pretty simplified approach. So um, it's not as straightforward as it used to be, for sure. And I think there is still potentially a role for baseload technologies, but they have to have the right price point and be a little bit more flexible, I think, for shutting down when prices are negative. All right. Well, it's 5 minutes past. Appreciate everybody who was able to stay a little bit longer. Thank you for your questions. And I look forward to seeing you at our next webinar. Good day for now.